Hi everyone, my name is Tan Chen Hao, and today I'll be talking about rotating reference frame, and this is part of a series of physics Olympiad videos that I plan to make, hopefully. Right, and this series of lectures is going to be covering more niche topics that most physics Olympiad texts don't go into, but I feel that it's important to have a solid understanding of all of physics in order to do well, because you never know when these niche topics might appear as well. Right, so today we'll be covering rotating reference frames, right? And we'll start off by discussing generally what what accelerating reference frame and yeah, so we'll be discussing about non-inertial reference frames first of all, right? And then we'll be we'll be focusing on rotating reference frames. Yeah, where in rotating reference frames you start to obtain fictitious forces such as the Coriolis force, the Euler force, and the centrifugal force. Okay, so but let's start talking about non-inertial reference frames first. So what is a non-inertial reference frame? Simply speaking, right, non-inertial just means that the acceleration is not zero. So the velocity is not constant. Okay, so what is special in a non-inertial reference frame? You may know the law, right, F equals ma, right, where F and A are vectors, right? So that means you have three components. If you're unsure about vectors, you can see my H2 Math series. So I'll put a link in the description below on my H2 Math topic on vectors. So yeah, so for vectors, right, F equals ma is a vector equation, but the caveat, right, is that this law, the second law, right, Newton's second law, only holds in inertial reference frame, which I'll denote RF from now on. So what is an inertial reference frame? Is one where the acceleration of the reference frame is zero, right? And that means the velocity is constant, right? And remember, acceleration is a vector, velocity is a vector as well. And that means that the velocity is constant, it's a constant vector. So the velocity is a constant direction and length, constant direction and magnitude. So what is a reference frame? A reference frame in physics is basically the idea about perspective. So yeah, so it's about perspective. So for example, right, I have a certain perspective of the world, right? And you have a certain perspective of the world. If let's say I'm stationary at a train station, then I'm at a stationary reference frame. Then if you're moving off in a train, perhaps you're accelerating off from the station, right, with the train, then you're in a different reference frame. And how we perceive physics, right? The numbers that we associate to let's say velocity will be different. So what I mean by this is, let's say a simple example, right? Let's say I'm standing still, right? And there's a ball at the train station. Then I will say the position of the ball is constant, right? It's not changing. It's at x equals to 0, y equals to 0, z equals to 0. But if you're moving off in a train, then you'll say, hey, actually the x coordinate of the ball is changing. Um, and I would say that it's because you are moving, but you would say that the ball is moving and I am moving. So yeah, so reference frame, in different reference frame, right? We might not, if two observers are in different reference frame, they might not agree on the numbers, right? On the some quantities, right? And in special relativity, it gets even more interesting when two observers actually cannot agree on the length of objects, right? And that seems very unintuitive, but it's actually true, right? In special relativity, right, the reference frame becomes even crazier. Yeah. Yeah, but so even though we're from different perspective, right, but the physics, right, should still hold true, right, in all reference frame. So physics should be independent of our choice of reference frame. Because if physics, right, it was different, then that would really, that would break down reality, right? Like things like cause and effect should still hold true. So yeah, it gets especially tricky in special relativity, but for this, in this case, you can just think of reference frame as a perspective. So so an inertial reference frame just means that a reference frame that is at constant velocity. Yeah, whereas a non-inertial reference frame just means that one that is accelerating. So F equals ma actually doesn't, it actually only holds, right, in inertial reference frame, because as soon as you're accelerating, right, you're gonna affect this acceleration over here. And yeah, and I'll put a link to description. I'll put a link to a video explaining why F equals ma only holds in inertial reference frame. So that one was from 801, right? So there's a 801 lecture, MIT lecture on classical mechanics explaining why this is so. And in addition, right, I will also so on top of that, I'll also put a link to my video, right, on question 6. So it's an example of a question that involves accelerating reference frame. And yeah, that one, I'll show you why choosing accelerating reference frame is actually simpler. It simplifies the equations of motion. So the key idea is that because physics should be independent of the choice of reference frames, right, you should be free to choose any reference frames to obtain the same physics phenomena. And as a result, certain reference frame, because they describe the activity, they describe like position differently, right? Certain different reference frame could have simpler equations of motion. And the idea is that if we can choose a reference frame where the equations of motion is simplest, then it simplifies our calculations much further while still making sure that we're calculating the same physics. Yeah, so I'll leave a link in the description below, right, on the question that involves using an accelerating reference frame. So yeah, anyway, with that, if you're there's briefly two ways that you could have non-inertial reference frame, right? So number one, you could have a non-inertial reference frame because you are accelerating linearly. So linear acceleration, right? And for that, I'll put another link, right, from 801 describing the force that you feel is actually just negative of the mass times the acceleration. So you end up feeling a fictitious force, right? Okay, I didn't talk about fictitious forces yet, but second case is when you're rotating. So then that is what we're going to cover today, right? That's the focus of today, right? And yeah, so the question, right, is that if the second law only holds in the inertial reference frame, if the second law only holds in A equals to 0 reference frame, then what happens, right? What happens, or rather, how do we do physics? Right? How do we calculate physics in non-inertial frames, right? Because the law breaks down. So how do we fix it? So the answer, right, is F equals ma is not true. But if we add some additional fictitious forces, we can add this additional fictitious forces, right? And that's why it's called fictitious, right? Because you don't observe it in an inertial reference frame. If we add these additional fictitious forces on top of the real forces that we exert on the object, then we can make this second law hold true. So what are these fictitious forces? These are examples of your centrifugal force, right? Centrifugals, your Coriolis force, and Euler force in the case of a rotating reference frame. So these are all under rotating frame, rotating reference frame. So yeah, so the F over here is the real forces, whereas but F itself is not equal to ma because we're in a non-inertial reference frame. But if we add on the fictitious forces, then this holds true. So today we'll be deriving, right? We'll be learning how to derive from first principles these fictitious forces. And I hope to let you have a strong understanding of the math behind it as well. Okay, so one small thing, right? Small digression. Centrifugal, you may hear of the term centripetal, right? And the difference between them is that centripetal force is not an inertial, it's not a fictitious force, right? Centripetal force with petal, P-E-T-A-L, is the force that is required to keep an object in circular motion, right? So if you swing a bucket around, right? If you swing a bucket around, then the rope provides the tension, right? And the tension is the centripetal force that's keeping the bucket in circular motion. Whereas for centrifugal force is a fictitious force that arises when you're in a non-inertial reference frame, right? So I covered this in a lot of detail, right? I covered this in quite a long video and I'll put it in the description below. It's called centripetal versus centrifugal. Okay, so so today we'll be deriving and we'll be coming across how the centrifugal force arises as well. So hopefully, if you come from that video, maybe you can understand this video better as well. Okay, so let me think if I have anything else to mention. Yeah, not really. Okay, so with that, let's move on to rotation. So how do we do rotation in physics, right? So let's just restrict ourselves to 2D rotation for now, right? Meaning that we have a XY plane and the Z-axis is just going to be out of the page. And then we have a rotated frame, X prime, Y prime. And this rotated frame will be rotated at an angle theta, right? So later we'll make this theta depend on time, and that's how we get rotating reference frames. But for now, let's just keep it at just keep it as a parameter. So now let's say so we have two reference frames over here. One is the fixed one, right? One is the fixed one, and one is the rotated one. So the purple one is the rotated one. So now the question is, if we have an event, right? If let's say we have an explosion happening at this point, right? So our fixed observer, our fixed reference frame will say that occurred at coordinates x, y, z, right? And how you'll find the coordinates x, y, z is you project it down onto the x-axis, onto the y-axis, and onto the z-axis. So this will be the x, this will be the y. And for the rotated observer, right, rotated reference frame, is going to be, they're going to say, hey, this happened to x prime, y prime, and z prime. And these are, to find that, it's going to project it down onto the x prime axis, right? And it's going to project it down onto the y prime axis and the z prime axis as well, but we don't draw that over here. So you can see the x prime, y prime, and z prime is a different set of three numbers from x, y, and z. Because clearly the lengths are different. You can already see that the lengths are different. So now what if we're given, right? If you're given this x prime, y prime, and z prime, how do we find? So if you're given x prime, y prime, and z prime, how do we find x, y, the corresponding x and y? So how do we find the x and y? So that's sometimes you note this as a coordinate transformation. So so if we have a x prime, y prime, and z prime arranged as a vector like that, right? You turn to vector notation. Then to obtain the x, y, and z, right? We can use a matrix, right, and multiply it. So we can take the matrix. So this is the matrix that we multiply to. So this is the matrix, right? We call it R. Let's call it R because it's a rotation matrix and it depends on the parameter theta. And we apply it to the position vector R prime to obtain the unprimed R position vector, right? So so this is how we go. If we're given this information, x prime, y prime, z prime, then we can calculate x, y, and z. Now the question is, can we go the other way? And the answer is yes, we can go the other way, right? If you're familiar with the matrix linear algebra, right, you know that a matrix can have an inverse if the determinant is non-zero. So we apply R inverse on both sides, and we apply R inverse on both sides, and that will give us, right? So this will give you the identity matrix, right? If you do a matrix, you do a transformation and you undo it, there will just be the identity. So it'll be 1, 1, 1 across the diagonal and 0 everywhere else. And that will give you your R prime. And so that means that X prime, Y prime, and Z prime can be also expressed as a transformation on the X, Y, and Z. And there'll be a big matrix over here. And so this this matrix, right, the R inverse, right, is going to be the inverse of this matrix. So how do we find the inverse of that matrix? I'll just give you the answer for now, but it's actually not too difficult to, there's a formula for it for 2 by 2 matrices. It's just this thing. So you can go ahead and check, right, that in fact, if you apply R inverse on R, right, this is R inverse, right, this is R inverse, and if you apply on R, right, this is R, then you get the identity matrix. Okay, so yeah, so one thing interesting to note here is that to obtain the R inverse matrix, right, is effectively the same thing as swapping theta for minus theta. So this is observation. This is an observation for 2D rotation matrices, which will say SO2. Yeah. So if you study further group theory and stuff, then you know that we call this rotation matrix SO2 for the special orthogonal transformation on 2D on 2 dimensions in 2 dimensions. So perhaps this is a good segue, right, to talk about group theory. So group theory digression. So I like to digress because there's so many interesting topics to talk about. So in 2D, right, in 2D, right, which we denote the group SO2, right? So what is SO2? SO2, right, is the group of all two-dimensional it's a group of all two-dimensional rotations. So perhaps you come across the saying that the set of all 2D rotations form a group, right? Or sometimes you may hear the additional adjectives like the Lie group, right? Or you might hear compact group or things like that. But yeah, so what's a group? It basically is a bunch of rules that these 2D rotations, instead of 2D rotations, must follow. So so SO2 is the group of 2D rotations, right? Which we give a name to the group, we call it SO2. And what is one law that you have to follow? One law is called a group composition law, right? And in this case, group composition is defined by if you have one rotation by theta, right? And if follow it up with a rotation by phi, then you're going, it's effectively, right, one single rotation by phi plus theta, right? So if you rotate something by theta and you further rotate it by phi, then effectively rotating the whole, doing one rotation by theta plus phi. So that should be quite intuitive enough, but yeah, that's what we call the group composition. So this is the composition law, right? And the group has other rules such as the inverse, right? So the inverse will be r minus theta, right? And r theta will give you r of 0. So if you rotate something by 0 degrees, then that's going to give you the original item. So this is known as the inverse, right, which we saw previously. And in addition to that, there's also some, yeah, so this is known as the identity, and there's some additional laws, but yeah, group theory is a very good subject as well. So one thing to mention is that SO2, right, is commutative, whereas, right, SO3 is not. So what is SO3? So SO3 is non-commutative. So what SO3 is, if you can guess, is the group of 3D rotations. So what is commutative? That means commutative means that AB equals to BA. So if in 2D, right, if you rotate um, by theta first and then by phi, then it's the same thing as if you had rotated first by phi and then by theta, right? Because it's just summation and summation is commutative. But that's not really true for 3 dimensions. And the reason is that in 3 dimensions, right? Imagine if you rotated something like that by 90 degrees in the XY plane, and then you rotated it up into the Z-axis, right? It's not the same thing as first rotating it up, right? Because if you rotate it up, then it's just effectively spinning it around, and then followed by a rotation is different. So you did A, right? Followed by B, it's not the same thing as doing B first followed by A. Yeah, and there are more interesting to discuss about group theory, but I don't think I should get too far tracked, right? But one additional thing is that SO3, right, is actually related to spin. So besides group theory, right, group theory defines a bunch of symmetries mainly. Yeah, group theory is a language for symmetries, and symmetries tell you, yeah, and symmetries are nice, but your symmetries can act on an object as well, and it turns out they can act on different kinds of objects. So in this case, we're just acting on vectors, right? But actually, there's a way for your rotations, right? SO3, right? For your rotations to, loosely speaking, act on complex numbers as well. So, those are known as representation theory. So group theory is closely linked to representation theory, right? Very, very interesting and rich topics in itself. And representation theory, right? I'll put a link in the description for my video on how the spin, right, arises from representation theory of this SU2. And SU2 is kind of like, loosely speaking, is kind of like 2 copies of SO3, right? But yeah, but there's a little bit too much. That's a little bit far away, far-fetched. So yeah. So representative theory comes in especially interesting in quantum mechanics, right? Where we are spin. So this is where you go to quantum mechanics is when all your representation theories start to pop up, or your linear algebra start to pop up, and yeah, so that's a really, really rich topic that I will encourage you to pursue, right? Group theory, representation theory, quantum mechanics, right? All very rich and interlinked topics. And yeah, and you also probably come across something called Lie groups, right? Because right now we see that our rotation matrix is parameterized by theta, right? And the question and the observation that we make is that theta is a continuous parameter. It's a continuous parameter from 0 to 2 pi, right? And then because it's continuous, right? It turns out that this group SO2, the SO2 group, is also a manifold at the same time. But yeah, okay, but enough of that, right? Too many interesting things to talk about. I can talk about it all day. Yeah, so let's go ahead and talk about, okay, so let's talk about, let's return to where we came from. So we left off by talking about how x prime, y prime, and z prime equals to your rotation matrix, the inverse of rotation matrix, right? Like this. Yeah, so this is where we left off. Okay, so now if we think, so if we want to transition to vectors, right? And to understand vectors, we first need to look at the unit vectors. So I'm going to draw a diagram here with the unit vectors. So this is my x and y, and if the So if I have the x and y, then I have the unit vectors I hat and j hat, right? And there's a k hat also in the z direction, but we don't draw that here. Then, so the I hat vector is simply 1, 0, 0, right? 1 in the x direction, 0 in the rest. The j hat vector is 1 in the y direction, but 0 in the rest. And the k hat vector is 1 in the z direction and 0 in the rest. Then, if I draw my x prime and y prime, right? Then my x prime will be I hat prime and y prime will be j hat prime. So yeah, so the thing we want to try now is we want to try to express I hat prime in terms of your I hat and j hat. So this angle is theta, right? So let's express I hat prime in terms of I hat and j hat. And the reason we want to do so is because our I hat prime later you see is going to vary with respect to time. So perhaps if I just do it now, right? Let's let our angle theta depend on time, and that's how we go from simply a rotation to the idea of rotating reference frame. So now our rotated reference frame, right? How much it rotates by our rotated reference frame has been upgraded, right, into a rotating reference frame, because now how much it rotates, it depends on time. And so at 1 second, right, it rotates this amount. At 2 seconds, it rotates even further. And that is basically the definition of a continuously rotating reference frame. So if you make it a function of time, then that's how we introduce dynamics. So yeah, so we're going to express I hat prime in terms of I hat and j hat. And the motivation, right, is because later we'll see that this one is rotating. It's a rotating vector. Yeah, so okay, so yeah, so we will also say that we're going to be working in the stationary frame. So throughout this entire chapter, right, we'll be working in the stationary reference frame. And what that means is that your I hat and your j hat, these are the fixed vectors. So the fact that we are in the fixed frame, it means that this I hat, j hat, and k hat, they are the ones that don't change. So let's just make it clear over here that I hat, j hat, and k hat are fixed, whereas your I hat prime, j hat prime, and k hat prime, they are the ones that are rotating. In this case, k hat prime isn't moving, but yeah, I hat prime and j hat prime are changing with respect to time. Okay, so how do we find the formula for I hat prime in terms of I hat and j hat? If we think of I hat prime as the I hat vector, so I hat prime, right, as a function of time is equals to the rotated I hat vector. So we want to rotate the I hat vector, right, by the rotation matrix R of theta. And since theta depends on time, let's put the time parameter in here now. So yeah, so I hat prime. So now, so this is our R of theta, right? This is our matrix. And if we apply, right, so this is effectively R. This is effectively R theta of time applied on the 1, 0, 0 vector. So we apply, right, it's essentially extracting out this column. So effectively extract out this column, right? And that will give us I hat prime of t equals to, okay, wait, hold on. I may have made a sign error over here. Yeah, so I made a tiny error over here. All right, this is not supposed to be R of theta. This is supposed to be R inverse of theta, right? Which is equals to R of minus theta. Okay, so we're back over here. So r of theta, right, is going to be cosine theta minus sine theta, right, and cosine theta. And all of these, they vary with respect to time. Let's not forget that. And then this is just 1, and the rest are 0. Apply a 1, 0, 0. And this is going to give us, cosine theta of time, sine theta of time, 0. So yeah, so effectively it's extracting this column, right? Effectively it's extracting this column. And yeah, so if you express that in terms of the I, j, and k, then we have I hat prime of t equals to cosine theta of t, I hat plus sine theta of t, j hat, right? And likewise, if we do the similar thing to j hat prime, then that equals to minus sine theta of t, I hat plus yeah, plus cosine theta of t, j hat. Okay, so yeah, so we see that our primed unit vectors over here, right? Our primed unit vectors over here, they depend on time. And how do they depend on time? They depend on time. Because the angles in their formulas depend on time. Theta depends on time. So why does theta depend on time? It's because we let it be, right? We let theta be a function of time, so that now our reference frame is no longer just rotated, right? It's rotating now. It's continuously rotating with respect to time. And yeah, so it's important to note over here, conceptually, that because we are working in the stationary reference frame, right, then our I hat and j hat, they are going to be constant. So because we are working the stationary reference frame again, right, then our I hat and j hat, they are constant over here, as seen over here. They're just 1, 0, 0, 0, 1, 0, and k is just 0, 0, 1. Whereas your I prime, your j prime, they are the ones that are rotating with respect to time. Yeah. So this is solely because of the fact that we're working in the stationary reference frame. Right? If we had chosen the rotating reference frame, then the rotating reference frame will see your I hat and j hat as changing, and the I hat prime and j hat prime as the ones that are stationary. That's if we picked the rotating reference frame, right? But because we're in the stationary reference frame now, your primed ones are the ones that are rotating. Okay, so with that, because these are depending on time, we're a bit curious, right? What happens if we take the time derivative? Right? What happens when we take the time derivative? What we will see. So if we go ahead and take the time derivative of the I hat prime vector, then because our I hat and j hat are just constants, then we're effectively just differentiating the components. So this is just theta, right? So this is just theta. How do you differentiate cosine of theta of t? We differentiate it using the chain rule. So that would be minus sine of theta of t. I hat, right? I hat is constant, plus cosine of t j hat, right? So then this is outside, it's a factor that's outside the entire thing. And this is actually simply j hat prime, right? And then there's this derivative which will denote by omega for now, omega of time. So omega of time is going to be, we're defining omega of time to equals to the derivative of the angle, right? And the angle changes with respect to time as well. So now, yeah, so let's do that for j hat before we make some observations. So differentiate minus sine, right? You get minus cosine. And differentiate cosine, you get minus sine. And since the I hat and j hat are constant, they just stay there. Okay, so now this is actually minus omega of t of I hat prime. Yeah, and yeah, okay. And if we do that to the k, right, then in this case it's going to be 0. Yeah, k hat prime does not change. Okay, so yeah, so what do we see over here? We see that the derivative, right, the time derivative, okay, I shouldn't use blue. The time derivative, let's use this blue. Time derivative of our changing I prime and j prime vectors, or changing I prime and j prime vectors, how do they change? What's their rate of change? Their rate of change is proportional to j prime and I prime. So the time derivative of I prime is actually proportional to j prime. So that's a bit suspicious, right? Like, how does that make sense? And let me draw a diagram to help it make sense. So let's say our I prime was like this, right? So what's the time derivative of it? The time derivative of it is j prime, which means that how it changes with respect to time is wanting to change by this amount, right? It's wanting to change by j prime, right? Scaled up by omega. So you see that because I prime and j prime are perpendicular, right? The fact that I prime and j prime are always perpendicular means that as I prime moves, right, j prime will also adjust accordingly, right? According to this equation. And in fact, you could say that they're kind of like coupled ODEs, right? They're kind of like coupled ordinary differential equations. Yeah, and that will mean that I prime is always going to just rotate in a circle. Okay, so if you go ahead and solve it, you realize that the motion of I prime, right, is just a circle. Yeah, I'm thinking if we should go ahead and solve the ODs, but I don't, yeah, I don't think so. It's so this if you substitute, you take the second time derivative, right? So you take another time derivative of this, then you realize that it maps to a SHM. It's kind of like a SHM for each of the components, and SHM is related to circular motion. So yeah, so okay, so let's not venture too far into the SHM part, the couple ODs part. But the key idea here is that I prime and J prime, right? How their rate of change is each other essentially, because for J prime, for J hat prime, his rate of change is going to be minus I hat prime, right? So you see that it's kind of going in a circle like that. So the motion is going to be like this. Okay, but there's a more neat way to put it in, right? And the more neat way is this. So let u, right? We introduce something called u, a vector u, and introduce a vector omega. Don't be too afraid, right? So we haven't defined what these things are. So u vector equals to either I or j, right? And omega vector equals to the vector with components 0, 0, and omega of time. So this one is a vector that depends on time as well. Yeah, so this is in a sense, this is a differential equation, right? Because it involves itself. So yeah, so we see a cross product over here, right? If you are not sure of the cross product, you can check out my H2 math video as well. Then the H2 math video on cross product. Yeah, so why does this work, right? So for example, if we let u equals to I hat, right, then substituting back into the equation, so I hat prime, sorry, I hat prime. Yeah, it's important, I hat prime, okay, it's not I hat. If we let u equals to I hat prime, then the derivative of I hat prime equals to this thing, where omega depends on time, cross 1, 0, 0, cross I hat prime, right? Which equals to 1, 0, 0 in the primed in the rotated frame. Then this is simply um, equals to omega of t k hat prime cross I hat prime, and that is equals to omega of t j hat prime. So we see that we have recovered the first equation over there. And if we let u equals to j hat prime, right? So if we let, another example, if we let u equals to j hat prime, then the time derivative of j hat prime equals to omega of t k hat prime cross j hat prime, and this equals to minus omega of t I hat prime. And we see that we recovered the second equation over there. And we try to substitute k hat prime, then we get k hat prime cross k hat prime is 0. So we see that right, we've neatly packaged these two equations. We've neatly packaged them into one form like this. Okay, so this will come in, why do we want to do this, right? Why would it come in useful later? It will come in useful because actually, if we had generalized the notion of rotation to one where the omega vector can be any direction we want, right? So we'll talk about this. Then the u can be any vector we want also. So ux, uy, uz. Then actually this holds true as well. So what do I mean? So okay, for the rotation first, let's tackle the rotation first. So for every single rotation, right, it can be shown that there's one axis that is not affected by it, meaning that the one axis, points along the axis are not moved. So that is known as the rotational axis. Axis of rotation, actually. Yeah, axis of rotation. And the axis of rotation, right? So the direction of this omega vector is equals to the axis of rotation. So yeah, so the direction of this omega is equal to axis of rotation. Now you might say, wait, the axis is axis, it doesn't have a direction, right? How do you choose the direction? So actually the direction of omega is axis of rotation following the right hand rule. So the right hand rule, right, states that if your thumb, right, you put your hand in a thumbs up like that, and then your thumb is the axis of rotation, right? It's a directional vector. The thumb is the direction of your omega vector, and then where your fingers curl would be the direction of the rotation. So if you flip your thumb, right, in the opposite direction, then you see that the direction at which you rotate by, it will have reversed, right? So at first we're going anti-clockwise. Now we flip it over, then we're going clockwise. So this omega vector, it encodes the direction, and it encodes the direction and the magnitude, right? So the direction, so the vector has a direction and a magnitude. The direction would tell you the axis of rotation, and the direction that it rotates by, it also follows from the direction of the vector according to the right hand rule. Then the magnitude, right? So the magnitude of the omega vector is equals to the rate of rotation. So you see that so this vector encapsulates everything we need about rotation. So any single rotation we want to describe, right? Any single rotation we want, we can describe it using this omega vector. So the first step would be to find the axis that it rotates by. Right. The second step would be to find the direction that is rotating either clockwise or anti-clockwise about the axis. Then, once we find our direction, we wrap our fingers around the direction, pointing in the direction that is curling by, and where the thumb points, right, is a direction of the vector. So that assigns a direction to the axis, and that will be the vector's direction. Then, how fast? The next information is how fast is it rotating by? That will be the magnitude of the vector. Yeah. So yeah, okay. Then for the u is any vector. So what does this show graphically, right? If let's say I have a omega like this, and I have a u like this. So omega is a vector, u is a vector. Then um, what's the time derivative of u? It's equals to omega cross u. And in that case, omega cross u, right? Actually, so omega cross u is actually, you do the right hand rule, right? For the cross product, is actually into the page, right? So yeah, so you can see that this is, it be always into the page, and the end result, right, is that you rotate around this axis like this in an anti-clockwise direction viewed from above. So yeah, if it helps, I should probably erase a little part of it. Okay, so let me just make it clearer. So it's going behind like this. Yeah. Okay, so now that's the power of putting in a vector form, right? So to recap what we've done so far is it's been quite a long road, right? Let's do a quick recap of everything so far. We first talked about non-inertial reference frame, right? It can be either linearly accelerating or rotating. The linear case, I'll put the link in the description below, right? But the rotational case is the one that we're going to follow for today. So if you have a non-inertial reference frame, then you need to modify Newton's law by some fictitious forces. And that's what we're aiming to derive today. So in order to derive that, right, the first step is to understand rotations. So you looked at the R matrix, right, and the R inverse matrix. Then we did a small digression on group theory because I like to digress to interesting things. Then we talked about uh, the rotated unit vector, right? I hat prime and j hat prime. And we let the theta now be a parameter of time. So by doing so, instead of just having a rotated frame, we have a rotating frame, right? It's now constantly in motion because theta depends on time. So then we saw that our unit vectors I hat prime and j hat prime depended on time, and it depended on time in this way. So we have closed expressions, right? We have closed formulas. We have formulas for how I hat prime and j hat prime vary with respect to time. Then we went ahead to differentiate it, right? And we found a way to neatly write it as this form. So we found a way to neatly write it like this. And why do we want to do that? Because it's easy to generalize to the general rotation case. So now we are no longer trapped in the 2D plane, in the XY plane, right? We're no longer doing the 2D case. Now we're talking about the full-fledged 3D rotation. Okay, so this is the formula um for so this is this formula describes um a rotating vector, right? But the vector has constant components, right? The vector has constant components. Um, yeah, okay. So now we are going to the reason why this is still limited, right? Because the constant components part put a huge restriction, because if we're talking about the position vector, then the position vector is of an object, right? Let's say a point particle. It's always going to be moving, right? So the components are not going to be constant. So let's go ahead and derive the case where we have a variable component vector, right? So once again, we're working in the stationary frame, right? And yeah, so in the stationary frame, right, our I hat prime of t equals to equals to okay, let's not go back there. So in our stationary frame, we'll describe a vector, a time varying vector f of t equals to f1 of t I hat plus f2 of t j hat plus f3 of t k hat. Yeah, by the way, I did not mention this at the start of the video, but the derivation that I'm following, right, the derivation that I'm following, basically the notes for this lecture, is the Wikipedia page. So I'm trying to go through the Wikipedia page, but I'm explaining each step a little bit more in greater detail and giving you the interpretation of the equation as well. So this, right, is the fixed frame. This is in terms of the fixed frame unit vectors. It's important to note that. Right, this is in terms of the fixed frame unit vectors. Yeah. Okay, but we don't want to describe it in terms of fixed frame unit vectors. So let's go ahead and change it to the rotating frame unit vectors. So this will be I prime, J prime, and K prime now, right? So because the ultimate goal is to we'll see why this is useful later. So we describe it in terms of the rotating frame unit vectors, right? A vector f of t. Where remember, right, I hat prime of t equals to cosine, actually not really, the rotate, remember that each one of them, right, I hat prime of t is equals to omega, the derivative of it is described by this, and likewise for the j hat and the k hat prime components. Okay, so yeah, so now our I hat prime and j hat prime is is defined to satisfy this differential equation where your omega of t, right, your omega vector is the vector that your reference frame is rotating by. And each one of those depends on time. So yeah, so what happens when we try to differentiate this time, this variable component, right? So now the components f1, f2, and f3 depend on time. What happens when we try to differentiate this vector? Right, it equals to, so f du f1 of t I hat prime plus by product rule, right? f1 of t di hat t dt, and likewise for the other components. Yeah, so in the Wikipedia page, right, they didn't put a prime over here, but they are still referring to the rotating reference frame. Okay, so after we have done the product rule, let's group it up into this term and the other term, right? And we'll see why later. So the purple term, right, first of all, the purple term, yeah, so, okay, so now in the purple term, to understand the purple term, let's go back into the rotating frame, right? In the rotating frame, right, remember that your I prime, J prime, and K prime were fixed vectors. So this is actually, in the rotating frame, the I prime, J prime, K prime were fixed vectors that do not change in time, right? Because you are rotating with because you're rotating with them, right? So this is actually just the derivative of f, reflect the time in the rotating frame, in the rotating reference frame. Yeah, so this is conceptually where it's the biggest jump, right? So this one, right? Over here, we're talking about the fixed frame, the fixed reference frame, right? Over here, we're talking about fixed reference frame, whereas over here, the df/dt is the rotating reference frame. And then that's for the purple term, and for the blue term, right? For the blue term, we can make use of the fact that that this property, right? di dt is equal to omega cross omega vector cross I prime, right? And same for the other components. To write it in the form of omega t cross f. So why is that so? It's by linearity. So what this means is that you see, right, your f1 di dt, right? I'll just ignore the heads for now. This one is equals to this one is equals to omega cross f1 omega cross I. So f1 omega cross I prime, then f2 dj prime dt equals to f2 omega cross j prime, and f3 dk prime dt goes to f3 omega cross k prime, right? Yeah, and then adding all of them up, if you add all of them up, then the f can be brought inside, right, by the linearity of the cross product. So this one is just omega cross f, right? And then the left-hand side is just your blue term, right? This is just your blue term. Yeah, so that's how we obtain this. So I'm going to spend some time to focus on this part. So if I bring this over a little bit, if I bring this over, right? Let me just bring this over a little bit over here, and right on the left-hand side, df over dt fixed reference frame. So this is important because we see that the purple term is this term over here, and the blue term is this term over here. And the distinction we see over here is that one is the rotating frame, right, and the other is the fixed frame. And what this means is that, and the reason for the discrepancy is that in the fixed frame, remember that I hat prime, j hat prime, and k hat prime were changing, right? They're changing with respect to time. That's why we had to apply the product rule, right? Whereas over here, in the rotating frame, I prime, j prime, I hat prime, j hat prime, and k hat prime are fixed, right? Because you're in the rotating frame, right? Yeah. So that's the key difference over here, right? And that's why from going from the fixed frame to the rotating frame, you pick up this additional term over here. So perhaps this equation might seem a little bit daunting. So let's go through an example, right? So let's say our vector f of t was simply t I hat prime, right? T I hat prime, I depends on time. Yeah. So in that case, right, df over dt in the fixed frame is equals to df over dt in the reference in the rotating frame plus, right, omega cross f. And let's just say that omega was 0, 0, 1. Okay, so then that will give us k cross I, that will give us j. So that will give us j So they'll give us P of j hat prime. Yeah, that's right. Okay, so that will mean that in the rotating reference frame, right? In the rotating reference frame, so let's first plot the direct. So in the fixed frame, right, we see this vector as rotating and growing in length. Right, it's rotating and growing in length like this. Whereas in the rotating frame, the vector is just simply growing in length. Right? So the difference between the two, right? So in the fixed frame, the derivative of the vector, right, which we denote in, let's say, blue, it looks something like this. Right? Whereas in the rotating frame, the vector is simply, the derivative is simply this. And that's where the P j hat prime comes in, right? The T j hat prime will provide the additional, in a sense, the additional change upwards, right? That will give you this kind of sloping, rotating behavior. Whereas in the fixed, in the rotating reference frame, you just see as a scaling. Yeah. Okay. So that's I tried my best to explain the difference between the fixed reference frame and the rotating reference frame. Okay, so with that, actually, we are nearly there, right? So all that's left to do, right, is to derive the rotational forces, the non-inertial forces, right, for rotating reference frame. We just need to let F equals to the position vector of a particle. So of course, this will depend on time. Yeah. So since the velocity, right, in the initial frame is defined as d over dt of r, right, in the initial frame, then yeah, so since that's true, then and this is actually equals to, so the I denotes fixed frame, the inertial frame, and then that, and in this case the R will denote the rotating frame. So this is R plus omega of time cross R, right? And just remember that all of these are vector quantities. I might not write them sometimes. Yeah, so then from there, the acceleration is simply the derivative of that. So you see that this one is the derivative in the rotating reference frame plus the omega cross, and we kind of pull out this entire thing, right? Kind of like a differential operator. Then this is simply that thing applied on it. So the thing applied on the velocity. So there'll be dr over dt in the rotating frame plus omega cross r. Okay, so to do so, we just distribute it. So the first one and the first one from the left one and the first one from the right one will give you d squared r dt squared in the rotating frame. The first one from the left one, second one from the right one will give you d over dt omega cross r, right? Which you can use the product rule to give you omega, okay, to give you d omega dt cross r plus omega cross dr dt. Right, and remember that this dt is in the rotating frame. Right, all the dt's here are on the rotating frame. Then the second one from the left bracket from the left term, and the first one from the right one will give you plus omega cross dr dt, and the derivative is in the rotating frame. And lastly, you get a term, two cross products, like this. Okay, so the left hand side is going to be d squared r dt in d squared in the inertial frame. Okay, so now let's do a bit of rearranging. So these d squared r dt squared in the rotating frame equals to d squared r over dt squared in the inertial frame minus, right? So there are now a few terms. So there are now a few terms, right? First term over here, this will be known as, so d omega over dt in the rotating frame cross r minus, so this is known as the Euler force. So the Euler force includes the minus sign, by the way. All the forces include the minus sign. Then the next one will be the 2 omega cross dr dt in the rotating frame. Right. So note that the subscript r is not meant to be the positional vector, but r is meant to be the rotating frame. Right. So this r and this r is different. This r vector minus. Okay. Lastly, we can use the triple product rule, right? So this will give us a quantity, right? Which will say it's okay, so let me try to remember it correctly. This will give us b a dot b. So first one dot plus one omega minus omega dot omega r. Okay, yeah, so that's that. So this second term, right, which includes a negative sign, is the Coriolis force. And this last one is the centrifugal. Yeah, okay. So the Coriolis force and the Euler force. Okay, so the Euler force is only there when you realize that the Euler force, right, is only there when your d omega dt is not zero. And that will mean that you are accelerating. So if you're just in a rotating, if you're just rotating at a constant angular velocity, then you wouldn't have the Euler force, but the other two forces will still be there, right? Yeah. So this is sometimes known as angular acceleration, kind of. No, not really angular. This is sometimes known as Euler force is sometimes known as the azimuthal acceleration. Sorry, not angular. Sometimes it's known as the azimuthal acceleration. Okay. And the centrifugal force is the force that throws you out on the Ferris wheel. Not the Ferris wheel, sorry, on the merry-go-round, right? So this one is kind of throws you out on a merry-go-round. And the Coriolis force, well, there's not really an intuitive way to understand it, but actually I can show you a picture later. But let's focus our attention on the centrifugal force for now, because we see the daunting, right? F centrifugal equals to m dot r minus omega dot omega r. You see this daunting term where all these are vectors, right? And there's actually a very nice geometrical picture to it. Yeah. So yeah, okay, actually, strictly speaking, this isn't the forces yet, right? But if we just throw in an M over here, then all of them are the forces already. So I'll just throw in the M everywhere. So I'll just throw in the M everywhere. Yeah, then now we can call them the force. If not, they're just the acceleration. Yeah, so I forgot to add in the M just now, just throw in the M. So what is this centrifugal force over here? So imagine if you have a omega like this and a R like this. Right? So omega is the one that's rotating around. So yeah, so the rotation will look something like this, right? Because by the d over dt r equals to omega cross r rule, right? It'll be going in anti-clockwise when viewed from above. Okay, so if you're viewing it from above, if this is the omega, then your r, the tip of r will be moving like this in this direction. Yeah. All right. So so what is the centrifugal force, right? So the first quantity, it helps to understand. So this centrifugal force, we want to understand the magnitude, right? But at the same time, we also want to understand the direction of this centrifugal force. So yeah, let's draw a vector diagram. So if we have omega dot r equals to omega is a scalar quantity. So it's omega, length of omega times length of r in the direction of omega, right? And then multiplied by the cosine actually. I forgot to mention the cosine. So it's actually cosine theta. Okay, and the theta is now the angle here. Right, it's no longer the rotation thing. Okay, perhaps I shouldn't use theta. Cosine phi. Okay. So this is the length, right? This is the length, and then the direction is this. Okay, and then you subtract away your length of omega squared, and then your r. Okay, so there's two things to pay attention over here. One is the length, right? These are lengths. The ones in blue are the lengths, and the ones in purple are the directions. So if we draw a diagram for what's happening over here, let's say we have omega like this, and your r in this direction. Okay, let's draw a little bit longer, r. So the length of omega times length of r cosine phi in the omega direction. So the first term, which I will denote in red over here, the first term is going to be something like this. So yeah, let's just call it 1. Okay, then your second term, I'll change the color. Your second term is going to be in a minus r direction. So it's going to be something like this. And actually, if you check out the length, right, they perfectly form a parallelogram. So this is actually a parallelogram. So if this is your angle theta, then this is actually your angle theta as well. And then, yeah. So how do we check the length, right? We know the length of one. The length of one is going to be simply omega squared r cosine phi, right? Oh yeah, I called it phi, not theta. So this one is going to be theta. This one is supposed to be, it's not supposed to be theta, it's supposed to be phi. Okay, and the length of 2 is going to be length of omega squared length of r. So you see that this one is the red one, right? The red one has length omega squared r cosine phi, and the orange one has the length omega squared r. And that's precisely, right, what happens when you drop the perpendicular down. So in fact, the resultant vector is just this vector, this one. And you see that this is going to be a right angle because this one is this hypotenuse and this is the adjacent to the angle phi, right? So the red plus the orange will give you the yellow. And yeah, so that's the yellow, right? And of course, it's scaled up by m, right? So so if you have a very large force, right? Yeah, basically the yellow one is the acceleration. So yeah, we've covered the intuition around the centrifugal force, right? The Euler force is basically your angular acceleration times your distance. Yeah, okay. So for the Euler force and the Coriolis force, perhaps it will help if I share my screen. Right. So if I share my screen right now, then you see that the Coriolis force is this force, right? If you look at this GIF over here, in the above, right, you're in the stationary reference frame. In the above, you're in the stationary reference frame, and the black ball is moving in a straight line, right? But if you're in a rotating reference frame, right, if you're from the perspective of the red dot, right, then you see yourself as fixed, and you see the ball is moving in a curved direction. And the curved direction is what the Coriolis force causes. Like the Coriolis force is the one that causes the curving of the black ball in the rotating reference frame. So yeah, so that's the Coriolis force. And for the Euler force, right, you can also check out the Wikipedia page. It's basically this thing, and yeah, it basically doesn't want you to accelerate in the direction you're going to. So yeah, you can. I'm not sure how to explain the intuition for this one. So basically it's the if you're riding on a merry-go-round, right? And the merry-go-round, the back of the merry-go-round, you're sitting in the seat, the back of the seat pushes you forward, then you're going to feel a force that once you that resists you going forward. It's gonna want to keep you where you are. So that's the best explanation. So it'll be the apparent force pushing the person towards the front of the horse as the ride comes to a stop. Right. So if the ride is moving, right, then as soon as the ride comes to a stop, right, as soon as your angular velocity changes, right, it decreases, then the Euler force is the one that makes you feel like continuing going forward, sort of like tangentially. Yeah. So yeah, and if the person is close to the parameter, right, then they'll receive greater apparent force. So yeah, so anyway, all the equations I've derived is from this Wikipedia article, rotating reference frame, right? In fact, I try to follow that storyline, the explanation. So yeah, I basically explained this Wikipedia page. So I hope that you've enjoyed this video. If you did, please leave a like and subscribe. It's been quite a long video. Have a nice day. Bye.